let's see what people think. What are the answers? 9% of people, I guess that's one person, thinks Alice is better. 2 people think Bob is better. But most people know that both Alice and Bob are equally good. They're equally good. Why are they equally good? Because we did all this stuff with Pythagoras, the Pythagoras for random variables, and we showed that when you are off, what matters is how far off you are from the mean, right? The amount you pay is the difference between what you think it is and the mean squared, plus the irreducible error, which is the variance of the dice. So both of them are going to pay $25 because they are off by 5. One of them is Alice is overestimating by 5 and Bob is underestimating by 5. But they're both off by 5. 5 squared is 25, so they're both going to owe $25 for being off on the mean, plus whatever the variance of the dice is. So maybe the variance of the dice is 10, so they both owe $35. Whatever the variance is, it applies equally to Alice and Bob. That's why both estimates are equally good. We're going to do the same problem one more time, but instead of dice, we're going to switch to coins. Coins. Dice have values. It's like regression. Coins have either heads or tails. And that is like classification, trying to figure out is it going to be heads or is it going to be tails. And before there was Alice and Bob, this time there's a type A coin and a type B coin. The type A coin is a 95-5 coin. It comes up heads 95% of the time and tails only 5% of the time. So out of 20 flips, only 1 flip on average is a tails. On the type B coin, it's an 85-15 coin. So it's 85% heads and 15% tails. And you want to know which is a better estimate. Should we say it's a type A coin or should we say it's a type B coin? We have an unknown coin and we flip it 10 times and we see this sequence. So it was heads 9 times and tails 1 time. And so the question is, do you think it's type A coin? Do you think it's type B coin? Or do you think they're both equally good estimates? Which type of coin do you think it is? So both types are equally likely. Type A is better, type B is better, or I don't know. So same exact question as the dice, except for now they're coin flips. And I'll let you think about what it is. So try to think of how would you do this in real life. I'll give you guys maybe say 2 minutes on your own, then we'll vote, and maybe we'll do a revote, depending on how the things come up. Okay, here we go. Okay, 20 seconds to put in your guesses. We'll probably do a revote, depending on what people say. Okay, time's up. Let's take a look at what people said. Counts. All right. 9 people think the type A coin is more likely. 3 people think the type B coin is more likely. 3 people think both types are likely. And 1 person says, I don't know. The correct answer is the type B coin is more likely. So most people were wrong. Most people were wrong. So I'll give you guys a minute. Try to do a little post-mortem. Why did you get it wrong? Is there a calculation you did wrong? What did you do? Talk to your neighbors. I'll give you guys like a minute or 2 minutes to talk for a bit. And then we'll take it up all together and we'll chat as a class. But most people were wrong. Most people were wrong. Okay, let's chat together as a group. Does someone want to tell me either why they thought the type A coin was more likely, or maybe they realized why the type B coin is more likely? Anyone have any nice ways to think about it? Or so, because I don't know was an option, right? You guys didn't choose I don't know. You chose type A. Why did you pick type A? Yeah.
If we go with type A, the occurrence of tails is less than 0.1.
Yeah. Okay.
So I think type B.
I see. Okay. So you're saying this is only 5% tails.
Yeah.
But in our sample, we had 1 out of 10 tails.
Yeah.
That's 10% tails.
Yeah.
And so, because we got so many more tails than we were supposed to get, that means type B is closer.
Yes.
But type B is 15%. So that's like, 10 you got 10%, and you got 5%, that's 5 below. You got 15%, that's 5 above. So they're both 5% off, right? Like for type A, we have too many tails. For type B, we have not enough tails.
Yeah.
Why is type B better?
Because I thought that it might have occurred that within the 10 times we toss the coin, there would have been chances that there would be no occurrence of tails. So type B would have more chances of getting the tails, instead of
type B would have more chances. Okay, I guess. Yeah, so I mean, if it's a type B coin, there's going to be more tails on average than if it's type A coin, right? But we saw 1 tail, and we got to decide. Obviously, if we saw 2 tails, for sure, we'd be like, oh, it's definitely type B, right? Because 20% tails is closer to 15 than 5%. If we saw no tails, we definitely say type A. And of course, I gave you guys the hard problem, where it's in between. It's exactly sort of between. And it turns out type B is a little bit more likely. But I mean, for me, they're both off by 5%. Yeah, were you going to say something over here?
So I was saying that for type A, the occurrence of tails for like 10 times, it should be 0.5. But 0.5 can't be it's not real. So when it goes above it, it will never be type A. It will be closer to type B.
Okay, so you're saying as soon as you're above 5% tails, it can't be type A anymore.
Yes.
So I want to give you a hypothetical example. Let's pretend we flipped 100 coins instead of 10 coins, and we saw 6 tails. Would you still vote for type B?
No, for that one it will be closer to type A, but here we are dealing with the range, the root of 0.5. So, and when considering it for type B, it can be maximum 1.5, but it can't be in this case. So it will be like the maximum it can go, it will be 1 tails. So
as soon as it's 1, it can't be type B.
Yeah.
Or it can't be type A. I think, for example, if we replace type B coin with a 16% tails, then type A would be closer. So the fact that it's kind of evenly in between, that B is getting the tie, so there's a tiebreaker or something, where type B is slightly winning, but the fact that it's higher than 5%, higher on its own doesn't matter. It really is something about the distance in some sense, and that really matters. Yeah, comment in the back.
Maybe the sample size is too small because in both type A and type B,
Yeah.
there is a higher probability of getting heads.
Right.
But very small probability of getting tails. That is why
Yeah.
tails matters more
Right.
than heads. And we only have one tails in the data set, but there is a higher probability
Right.
of getting a tails using type B.
Mm-hmm.
And since we only have one, it might be possible that maybe the sample size is too small.
Yeah.
And if we collect 1,000 data points,
Yes. So of course, I think that this is a great comment. The sample size is quite small. I think that is saying that we're not really sure either way. So we're trying to say which one is better or worse. And the one that's better is only going to be very slightly better than the other, because we're kind of like blind. Like, we're like, oh, it could be type A, it could be type B. It's pretty close between them. If we had more data, we would be more confident about which one it is. It's a little bit like the dice rolling problem. If you roll the dice 3 times and you have the mean, is that a really good estimate of the true mean? No. Like, I bet the more you have, the better you will be. So that's definitely true. You had something to say about 1 tails being more likely for type B than type A. Is that right?
because 15% probability of tails in type B.
Yeah. This is true. So if you calculate for a type B coin, what is the probability of having this sequence? You can calculate that probability. For a type A coin, you can calculate this probability. We can compare the numbers. Let's compare the numbers. Did anybody use a calculator and have real numbers, or is everyone just thinking? Did anybody do a number, like like grade 4 math? Type the numbers. Nobody did. Okay, let's do it now. How do you do numbers? You can use Google, but Wolfram Alpha is a very nice website as well. Let's calculate the probability for a type A coin. What is the probability that a type A coin will have 1 heads? How would you calculate it? Sorry, 1 tails. 9 heads and 1 tails. Yeah, go ahead. Yeah, you just multiply it out. So we got, first we got a heads. Let's see what we got. We got heads first. What was the probability of heads? 95%. So first number, 90.95. Second number, heads, times 0.95. 0.95, not negative 0.95, times 0.95. Third thing, heads, right? The third thing we got was a heads, 0.95. And so on, right? In fact, look, it doesn't really matter the order they're in. It's going to just be a bunch of heads, each of which are 0.95. How many heads are there? There's 9 of them. So why don't, instead of multiplying it out 9 times, I say to the power 9. To the power 9. Okay? And then there's 1 tails, and the tails is 5%. So I multiply by 5%. So this is the probability that a type A coin will output the exact string we saw, right? What's the probability of getting heads, tails, heads on a type A coin? It's this number. 0.95 to the power 9 times 0.05, and Wolfram Alpha has calculated this very nicely for us, is 0.031. So 3.1% to get that exact sequence of heads and tails. That seems like a small number. You might remember that if you ask what is the probability of getting 9 heads anywhere, you would have to multiply this by 9. So the probability of getting, oh boy, what did I do? Okay. The probability of getting 9 heads and 1 tails is 28%. So when you flip a type A coin, if you flip it 10 times, 28% of the time you're going to get 9 heads and 1 tail somewhere, and 3% of the time you're going to get the exact sequence we saw. Okay, that's the type A coin. Let's make a new tab for the type B coin. The type B coin, 0.85 to the power 9, this is 0.85, times 0.15 to the power 1. And it's also around 3%, but it's a little bit bigger. So for the type A coin, the probability was 3.1%, and for the type B coin, it's 3.47%. And that is why the type B coin, you would say, is a little bit more likely. And again, these two numbers are very close together, right? So if we had a really big sample size, maybe one of these numbers would be a lot bigger than the other one. In this case, they're both very close, but the type B wins by a little bit. Let's do a hypothetical type C coin, because I want to check the thing I said before. What if it as a type C coin that was 16% tails? Let's check that one. That would be 84 to the power 9 times 0.16. Oh, okay, that's still more likely than the type A coin. Okay, look at that. So no, I want it the other way around. 84, yeah. This is still more likely than the type A coin. Okay, that's interesting. Okay, but of these options, let's just go back to the original problem, type A and type B. Type B is more likely. This thing is called the likelihood. We just calculated the likelihood of getting the outcome we saw. So we have these hypotheses, and under each hypothesis, we have a likelihood for the outcome we saw. And what we've just done is we've done the maximum likelihood. So type B is a better choice because it has a higher likelihood. And you really have to get out your calculator and calculate these things. Question in the back, yeah?
Do we really need to calculate the likelihood? Because in my opinion, the type A 0.0.9 file divided the 0.05 is 19, and the type B, the 0.8 file divided the 0.15 is 5.67, and the real results, the proportion is 9, so the type B is closer to the 9, so to the type B.
Okay, so you're saying there's like some way you can tell which is bigger without actually typing it in your calculator?
Yeah.
Okay, yeah, so probably you could do that. Yes, in fact, for sure there's all sorts of smart ways you can like figure out, like if you didn't have a calculator, which number is bigger. And I'll show you the graph in a minute. The graph, if you look at the graph, you can see instantly which is bigger. But fundamentally, you're doing some kind of proxy for calculating the number and saying which one is bigger, right? So you're doing it in a smart way, which is great. But like fundamentally, this is the choice to be made is which of these numbers is bigger. One way to see which number is bigger is type it in your calculator, see which is bigger. There's other smart ways to do it as well. I totally agree with what you said. But that's what we're doing. So we're going to do this likelihood. And the thing I want you to really realize that is very different than what we were doing before is that it's not symmetric anymore. So when we did dice and we did regression, it was symmetric. The only thing that mattered is how far away you were. If you're 5 over or 5 under, doesn't matter. It's the same. You're off by 5. Nothing else matters. In this one, it's all wonky because it's not just like the distance, right? It's some kind of funny thing that involves expressions like this. P to the power 9 times 1 minus p. How does that behave? In this one, so this is a much more complicated function than just the difference squared. Okay, so before we were kind of playing with like polynomials, the difference squared is like what you learned in grade 10. Now we're going to have logs and stuff, all sorts of funny things. So let's do a little bit of exploring here on what this number is. And one thing people do, this likelihood, these numbers get very small very fast. So you saw they were already like 3%. You can imagine if we flipped 100 coins, it would be like 0.00000. There'd be a bajillion zeros in front. And so what people do is they take the log. So the log converts very small numbers, like 10 to the minus 8, it converts it into minus 8, right? Minus 8 is a number I can understand. 10 to the minus 8 is like too many zeros, okay? So we're going to take the log, and we're going to look at the log. So this is called the log likelihood. Let's start a new page here. So the likelihood, and this is under some estimated probability p hat. So for example, the type A coin, p hat was 95%, put 0.95, and the type B coin, p hat was 85.85. And the likelihood for some observation is p hat to the power, let's call it xi, times 1 minus p hat to the power 1 minus xi. And so here xi is either 1 if it's heads and 0 if tails. And that is one observation, right? if xi is 1, then you get a p hat. And if xi is 0, then this term goes away, and you have 1 minus p hat to the power 1. So this is a funny way to write p hat if xi equals 1, and 1 minus p hat if xi equals 0. So if you get a heads, you get a p hat. If you get a tails, you get a 1 minus p hat. And we multiply all these together. You do the product over all of your data and data. So this is the likelihood. And now I'm going to take the log to do the log likelihood. This is called the likelihood. Let's call it the like. That's good. What is the log like? And I'm going to do the natural log because that's what I like to do. When you do a log, a product turns into a sum. So you have the sum from I equals 1 to n data. And when you do the log of this guy, the log of a power, the power jumps down. So you have xi to the log p hat plus 1 minus xi to the log of 1 minus p hat. So that's where this formula is coming from. We just took the likelihood and we took the log. Any questions or comments about that? The first time I saw this with this funny power business, right? It's really a funny way of writing p hat or 1 minus p hat, but it makes this next formula very nice. So it maybe takes a little bit of time to get your head around that. Any questions or comments around that? Okay. So another way to write this is a great formula, by the way. This one is a good one to write down and remember forever. Another way to write this is you could write this as the number of heads times the log of p hat plus the number of tails times the log of 1 minus p hat. And that's because every time there's an xi, when you add them up, you're doing 1 plus 1 plus 1 plus 1, you're adding them all up, that's the number of heads. Every time you do a 1 minus xi, you add them up, that's the number of tails. That's an equally good way to write it. And let's draw a graph of this as a function of p hat. This is some function that depends on p hat. For every different p hat, you get a different value. And you can see what does this graph look like. All right, let's look at the graph. I'm going to make it in my favorite graphing calculator, Desmos. Let me click. By the way, guys, Desmos now has a 3D version. Should we use the 3D graph? Probably not today. Okay. Probably we'll stick to the 2D. Okay. So here's the graph. The number of heads we saw was 9. The number of tails we saw was 1. And I'm going to look at the function, which is heads times the log of p hat. I'm going to call p hat x, because Desmos always thinks x is the input. So I'm going to call that x plus tails times the log of 1 minus x. And there's the graph. Okay, there's the graph. Let's zoom in properly. We care about x values. Those are p hat's estimated probabilities between 0 and 1. 0 and 1. And it looks like the values are quite negative. Of course, it makes sense it's quite negative. We saw it was like 0.03. If you take the log of a tiny number, you get a negative number. So let's go down to the negative numbers. It should never be too big. Let's go from minus 5, say, to 0. Okay, it's all the way over there in the corner. So this is what the graph looks like. Let me zoom out a bit. This is what the graph looks like. It's some kind of funny graph like this. So the x value tells you what is your estimate, and the y value tells you what is the likelihood. The maximum likelihood is the top there. Where do you guys think the max? Does anyone want to take a guess? Where is the exact maximum of this function? What value of x, what value of p hat has the maximum likelihood when you see 9 heads and 1 tails? Anyone want to take a guess? Yeah. 9. Let's try x equals 9. Oh. X equals 9 is not right. X equals 9 is all the way over there. But you're on the right track. You want to try again? How would you fix 9? 0.9. 0.9! Yeah, that is a much better guess. 0.9. Okay, here we go. Let's zoom back in. Is it right at the tippy top maximum? It is. So 0.9 is the maximum likelihood, right? And this curve, you should really think of this curve. This is just like when we were doing the quadratic equation, right? A quadratic equation would be like negative x minus 0.9 squared. This would be like, okay, I gotta multiply it by what? By 2. Where's my graph? Oh, there it is, okay. Minus, let's say minus 2 or something, right? When we were doing mean squared error, your loss function is a quadratic, and you want to try to find the maximum. Now we're doing these likelihood things, and it's not a quadratic, it's some funny shape. That's the point. Okay. So the maximum is at 0.9. In the question I said, what is bigger, 0.95 or 0.85? So if you call this function L of x, L for likelihood, or log likelihood, then you can plot what is 0.95 and L of 0.95. That'll be some point, if you do it correctly. There's 0.95, the type A coin, and here's 0.85, comma L of 0.85. And they are both 0.05 away from the maximum, but one of them is a little bit higher than the other one, right? And that is why the type B coin won. So like a little bit higher up, a little bit more likely. And why is it a little bit higher up? Because the whole graph is completely asymmetric, right? The graph, when you smoosh it towards 1, it goes down to 0 really fast. That's saying if you had a coin that was like 100% tails, or 100% heads, you would never ever see 9 heads and 1 tails. So sort of the closer your coin is to a pure heads coin, the more unlikely this is to see. You have this like steep cliff over here. Okay. This loss function, so far in the course we've been doing mean squared error was always our loss function. This loss function is called the cross entropy loss. This graph is called the relative entropy between the p hat value and 9 over 10. I will say one other thing is people often normalize it. So instead of doing heads and tails, this is the total likelihood. You could do the likelihood per coin flip. That would be just dividing everything by 10. So you could do this whole thing divided by heads plus tails. And now you get a graph where if you flip more coins, you still maintain the same scale. And this really is the relative entropy. So I'm going to make this definition over here. This likelihood, if you divide it by the total number, so if you do 1 over n data times the log likelihood, this thing is called the relative entropy, or the cross entropy. All right, well, let's call this the cross entropy loss. It's this thing, so it's 1 over the number of data points, and then you do the sum, I equals 1 to n data of xi times the log of p hat plus 1 minus xi times the log of 1 minus p hat. And this is really very similar. You should compare this to the mean squared error loss that we had before earlier in the course. That was 1 over n data. And that was the sum, I equals 1 to n data. And that was, I guess that would be something like xi minus mu hat squared, right? You estimate the mean, and then you do the difference between the mean and what you observe squared. You add that up and take the average. That was the mean squared error. Now instead of doing this, we're doing this thing with the logs and stuff. Other than that, they're very similar. I should have called it y instead of x, right? Normally we think of x as the thing that helps us make our estimate, but the values here are the things we are estimating. So let me go back and change them all to y's. Well, okay, I won't change them to y's, but they really should have been y's. They are the observations here. There is one significant mistake on the board right now. There's one thing I forgot to write. Does anyone know what I forgot to write? So right now it's not correct. It's almost correct. But there's a super annoying thing that you must always remember.
Irreducible error.
The irreducible error. Yeah, if you took the expected value of this, then the expected value of xi minus mu hat, right? So if you did the expected mean squared error, then you could write that as mu minus mu hat squared plus the variance of x. So when you take the expected value of this, there is an irreducible error that pops out. That's true, but on its own, it's just written like this, and then the irreducible error just pops out when you take the average. So it's not that. I'll give you a hint in graphical version. So this in green right now is the log likelihood. In green right now is exactly this formula. Let me plot the same kind of formula that I have written over here for the squared loss. So the squared loss says you do something like x minus the true mean. Let's pretend the true mean was 0.7 squared plus the irreducible error. Let's pretend the irreducible error was 2. Okay, so there is that thing. So do these both look like loss functions? What does a loss function mean? A loss is like how bad you're doing, right? You want to minimize the loss function, right? This green curve, I'll tell you how to minimize this green curve. You make a guess like x equals 0, right? So this is the likelihood. The loss function is not the likelihood. Likelihood, you want to make it as likely as possible, and you maximize your likelihood. Loss, you want to minimize your loss. What is the relationship between likelihood and loss? There's a negative sign. So right now, the green curve is the likelihood. If you want it to be a loss function, you must put a minus sign. You must put a minus sign. And this is something very easy to forget. There should be a minus sign here. The cross entropy loss is not the likelihood, it is negative the log likelihood. And the mean squared error loss, it turns out, is also the negative log likelihood. The negative log likelihood. 1 over n data times the log likelihood. It's the negative log likelihood when you have Gaussian random variables. So if you have a random variable whose density is e to the minus 1/2 x minus mu squared, then when you do negative the log likelihood, you get exactly this thing. There should be a factor of 2. Sometimes people leave the factor of 2 out, so I will also leave the factor of 2 out. Okay, so that's important. Loss and log likelihood are almost the same, except they're opposite signs. If you want it to be a loss function, you must multiply by the negative sign. It's very easy to forget because there's no negative signs here. The negative signs are baked into the fact that the p's are less than 1. Okay, let's go back to here, and let me put a negative sign. So we have, that's the L for log likelihood. Let's make it a capital L for loss, and then I'll do negative. Now it really is a loss function, and you really should think of it in the same way as the square loss, except it's a lot more difficult because it's not symmetrical. It has this funny shape that is not symmetrical, but you still want to minimize it. There's still a minimum possible value, right? The y value here at the minimum, that's like the irreducible error. That irreducible error in this case, it turns out, is something called the entropy of the coin flip. So this amount of irreducible error is not the variance anymore, like it was before, it's the entropy. I won't go into super lots of details about that. So this is really fundamentally the difference between regression and classification, is before we were trying to minimize the mean squared error. In classification, we're trying to minimize this new thing, the cross entropy loss. And this is when we're trying to estimate the probabilities of things, that type of classification where you first estimate the probabilities. This is a good time for questions or comments. Anyone have any? Okay, so this is what we're doing today. We're doing this second type of regression. We're doing the probability of class estimation. We're trying to estimate the probabilities. So something happens. Sometimes it went heads, sometimes it went tails, sometimes it was red, sometimes it was green, whatever. And we're trying to estimate what is the probability that it does each thing. And the way we're going to do it, we're going to use this cross entropy loss, not the mean squared error loss. Because the mean squared error loss is appropriate for things that have that come with this type of Gaussian distribution, whereas the cross entropy loss is appropriate for heads and tails with p's and 1 minus p's. Okay, so let me write out the exact setup that we're going to do and what we've done so far. So our goal okay, I'm going to do a little 2-column table here. On the left table, I will put regression, which we've been doing so far in the course. And on the right, I'll be putting classification. And just to emphasize, I'm going to say we're doing classification by actually estimating the probability. Right? Because you can do classification without estimating the probability. That's what we did last class. You just say, I think it's heads, I think it's tails. This time we're saying, we're going to try to estimate what is the probability it's heads. And so it really is, we've taken a classification problem and we've turned it into a new type of regression problem, right? Regression means estimating some variable. Right now we're estimating the probability. Okay? So our goal in both our goal for both of these is to estimate something. In regression, we're trying to estimate the mean. Mu hat is some real number, mu hat. And in classification, we're trying to estimate the probability, p hat. And p hat is some number in the range 0 to 1. Okay? And in general, you might have multiple categories, right? Maybe you have 3 categories. Then there would be 2 p hats. There would be p hat for the first one, p hat for the second one. The probability of the third one would be 1 minus the first 2. We're going to start with just 2 classes at a time. So to start with, we're going to do 2 class. And that makes things a little bit easier to see because there's only one number. Of course, we could have done that with regression too. You could say, I'm trying to estimate the height and the weight of the person. But to keep things simple, we're doing one number at a time. So this is our goal, is to come up with these things. And how do we measure how well we're doing? We use the loss function. The loss function. Okay, and for regression, we use the mean squared error, the MSE, which was this formula, 1 over n data. And it was the sum, I equals 1 to n data. And we do xi, okay, now it really matters, the y's and the x's matter. Yi minus mu hat of xi all squared. Right, so you give me xi, I estimate the mean based on what I saw. You tell me xi, I estimate mu hat of xi. And then we take the true value and we subtract them out and square them. That was the loss function. And we talked all about how there's a training set and a test set, so you can calculate this value on any set of points xi and yi. And you want this mu hat function to input x's and output y's in such a way that your loss is minimized. That was the mean squared error. For coin flips, it's the same setup, but now you have the cross entropy loss. The cross entropy loss, which is the same kind of formula, 1 over n data. And you have sum from I equals 1 to n data. But what do you have? You have this really funny looking formula, yi times the ln of p hat of xi. So for some given xi, you estimate p hat, you do this, you add on 1 minus yi times the ln of 1 minus p hat of xi. And this is coming from the log loss. Am I forgetting anything? The minus sign, yes, very good. Don't forget the minus sign. It's so easy to forget the minus sign because it looks, you want it to be positive. I didn't write any minus signs here, but they're secretly minus because the log of a tiny number is negative. So you have to put the negative sign there. So that's the setup. It's very similar. And this works for any type of regression. Like you could have some crazy complicated system for estimating mu hat or p hat. But we're going to start with linear regression. Linear regression. So linear regression. What is linear regression? It's just saying I'm going to try a very simple function. Mu hat of x is just going to be some constant beta times x. Or in general, x will have many components and you do a linear combination of all of them. But if it's one dimensional, it's like that. So linear regression just says, look, we're going to try to do this minimization, and we're going to use a linear function to do it. This is comparing to the topic we're doing today, which is logistic regression, which is on the same kind of thing. It says p hat of x is also going to take on a very specific type of formula. Okay? And that is what logistic regression is. So in the same way linear regression says, I'm going to try to estimate, minimize this loss function using a special type of function. We're going to try to minimize this loss function using a special type of function. And the people who chose the function, they chose the following weird thing. They made this special function sigma, and then they do sigma of beta x, where sigma of x is equal to e to the x over 1 plus e to the x. This is called the logistic function. And sigma converts, so sigma inputs numbers in R. It can input any x value between negative infinity and infinity, and it outputs numbers in the range 0, 1. Right? So it's e to the x. If x is a big positive number, that's a big positive number. But then you divide it by 1 plus e to the x. That's just a little bit bigger than e to the x. So you take a positive number divided by a number that's a little bit bigger than it. That will be a number between 0 and 1. Okay, so that's logistic regression, and that's why it's called logistic regression, because you use the logistic function, and then you stick on, inside of it, you stick in the parameter beta. Okay. Any questions or comments about this setup? In the rest of the class, we're going to do some little details and see why they chose this function. Why did they choose the function sigma? Why did they choose a function people have heard of? Some crazy function. Why did they choose it? There's a very good reason, and you'll see why in a minute. But any questions or comments so far? Okay, before we do too much, I want us to do some practice with this function sigma, because it really is a very nice function for converting real numbers into probabilities. And it's used all the time in machine learning and things like that. This is anytime somebody says, I'm going to come up with a number between 0 and 1, what they actually do is they come up with a number in R, like any real number, and then they just apply this function to it. So it's really worth your time to practice doing it a little bit. Before I set you guys loose, I'm going to give you a problem. I want to tell you what it has to do with odds. So if P is a probability, that's a number between 0 and 1. So let me write it like this. Let's write P is in 0, 1. Did I spell probability wrong? Probability, okay. P is in 0, 1. That's what people, when you go to school, you learn about probability, 0.5, 0.75. When you go to Las Vegas, they don't talk about probability, they talk about odds. They say something like 7 1/3 to 1 odds. If you go and you bet on a boxing match in Las Vegas, then if I'm boxing a real good boxer, then the odds that I will win are 7 1/3 to 1. I will beat the other guy 7 times for every time he beats me. No, it'll probably be the other way around. Actually, it'll probably be like 100 to 1. But so this is, if we ran it a lot of times, we expect the event to happen 7 times more often than it doesn't happen. It's the ratio of how often it happens to how often it doesn't happen. That is P divided by 1 minus P. And P divided by 1 minus P, it can be a number, it can be as large as you want. It can be 100 to 1, it could be 1,000 to 1. But it's always positive. So this is in 0 to infinity, right? It could be all the way up to infinity. These are called the odds. For 7 1/3 to 1, that is an 88%. You can calculate 0.88, 88%. If something happens 88% of the time, then it's 7 1/3 to 1 odds. It happens 7 1/3 times as often as it doesn't happen. And there's something you can do with the odds, is if you're a mathematician, you see positive numbers, and you say, I take the log of that. That's called the log odds. The log odds. So you do the log of P divided by 1 minus P. If you do the log of a positive number, if it's bigger than 1, you get a positive number. And if it's between 0 and 1, you get a negative number. So this is between minus infinity and infinity. Those are the log odds. The log odds so I have to take the log of 7 1/3, the natural log. And 7 1/3 has the property, if you do the log, it's right around 2. So this is like 1.9999. I'm going to say approximately 2. And that's because E squared is approximately 7 1/3. Okay. So if you take the special magic number E, and you do it squared, it's about 7 1/3. So something with a probability of 0.88 has odds of 7 1/3 to 1, and it has log odds of around 2. And this log odds thing is exactly what the sigmoid function is doing. The sigmoid function is the reverse. It turns log odds into probabilities. I just showed you how to turn probability into log odds. But if you do the sigmoid of 2, so plus 2.0, that will be approximately 0.88. So the sigmoid function is the reverse. This is how you convert probability into log odds. Log odds into probability is exactly the sigmoid function. So the sigmoid, how should I say it? Let's say the sigmoid of log of P over 1 minus P. Those are the log odds of P. That is equal to P. So this is kind of why it's not too crazy, this sigmoid function. It has something to do with these log odds. Okay, let me set you loose to answer a question about log odds and sigmoid functions. Here are three questions about sigmoid functions. And I'll let you guys think about it. Yeah, and it might help you if you want to think of what does the graph look like. That might also help you for some of these. I'll show the graph in a minute, but maybe it's more exciting if you try to answer the question and then I show the graph. So take 2 minutes to try to do these basic things so we can get a handle on what the sky looks like. Okay, there's like 20 seconds left. Who needs more time? I'm happy to give more time if people. Everybody. Okay, fantastic. Let's give you guys some more time. Okay, so lots of people haven't answered yet. Let me give a hint by showing the graph, right? This is, I think the graph will answer a lot of these questions. So it's the graph e to the power x divided by 1 plus e to the power x. And of course, it lives between 0 and 1, exactly like we said. So I can make the y-axis. Let's make it go from negative 0.1 to 1.1. And you can see the function always lives between 0 and 1, right? No matter what x is, the probability t is between 0 and 1. And it has this thing, it smooshes down to 0, then it rises for a bit, and it goes up to 1. And you can see the symmetry in this function, right? There's some symmetry between the negative and positive values that might help you with some of these questions. I can also plot the log odds function. The log odds function is this function x divided by 1 minus x, right? This converts a probability into an x value. This is the opposite. And so this one, to see this one, you should make your y-axis a lot bigger. Minus 5 to 5, and there you go. So what is the relationship between the red function, which inputs things between negative infinity and infinity, and outputs things between 0 and 1, and this function, which inputs things between 0 and 1 and outputs things between negative infinity and infinity? How are those two functions related? Okay. How many answers am I up to? 14. Let's give 30 more seconds, and then I will take it up. Again, always feel free to put in, I don't know. That's a good signal to me as well. I said 30 seconds. Okay, time's up. Let's take a look. What did people say? Reveal counts. Sigma of 0 equals 16 people said 0.5. 0.5 is the correct answer. You can see it also on this graph. Where does it touch here? It's at 0.5. And that's because you have e to the 0 is 1. So you have 1 divided by 1 plus 1. 1 divided by 2 is 0.5. So very well done there. It is a fact that sigma of plus 2 is 0.88. That's what I talked about already. And using this fact, you can easily see that sigma of minus 2 equals, so of course you could just ignore the fact and calculate, but there is a relationship between plus 2 and minus 2. They are negatives of each other. What is the relationship between the probabilities? So it's not that it's still 0.88, but it is true that it is 0.12. So most people got that one right as well. How do you get 0.12? It is 1 minus 0.88. And you can see that also in the graph, right? If you have a number and you have a negative of that number, the graph rotates. The distance to 1 is the distance to 0 on this side. They are opposites of each other. So you could write that down as a fact, as something like sigma of negative x is equal to 1 minus sigma of x, right? And this follows because sigma of negative x is e to the minus x over 1 plus e to the minus x. What is 1 minus sigma of x? It's 1 minus e to the x over 1 plus e to the x. And if you simplify that, you get 1 over 1 plus e to the x. Okay. Doing 1 is 1 plus e to the x, subtracting e to the x is just a 1. Why is it true that 1 over 1 plus e to the x is the same as e to the minus x over 1 plus e to the minus x? You can multiply the top and the bottom by e to the x over e to the x. And then it will convert. E to the minus x times e to the x will be the 1, and on the bottom here, you'll have the 1 plus e to the x. So you can prove it mathematically, or you can just look at the picture and see. Another way is to think of odds, right? If the odds are 7 1/3 to 1, then the reverse of that would be 1 to 7 1/3. That would be the 1 minus the probability, right? If something happens 7 times more than the other thing, if you reverse it, then you're doing 1 minus the probabilities. You're just switching the event and not the event. And reversing the odds is doing the reciprocal of p over 1 minus p. You're doing the reciprocal. And doing the reciprocal inside a logarithm is multiplying by the negative. So there are many different ways to see this fact. Last but not least, I gave you the hint that sigma of log of p over 1 minus p equals p. Right? If you do the log odds and apply sigma, you get back p. This question is asking you the opposite. Right? If you do log of sigma of x over 1 minus sigma of x, the answer is just getting back to x. How many people got x? Half the people got x. Okay. And this is true. This one is true, but that will be equal to x. So doing the log odds and then doing sigma, or doing sigma and then doing the log odds, both are doing nothing. You get back where you started. And you can see that in the picture, the blue function and the red function are inverses of each other, right? They undo each other in either order. Okay, so now we know we're comfortable with this sigmoid function. Maybe it seems a little bit less crazy where it comes from. And now I want to talk about linear regression versus logistic regression. This is another good time if there's any questions or comments before we do this. So in the next little bit of the class, you're going to learn what happens inside the computer when you say, please fit the linear regression. Right? Up until now, it's been sort of magic. You just say, we're doing linear regression, we know what it is, and we tell the computer, please go do it, and the computer comes back and says, I think beta is 1.7. And you're like, okay, pretty good, let's keep going. How did the computer come up with 1.7? Why not 1.8? Right? How does the computer calculate the value of beta that it thinks is true? That's what we're going to learn. Okay, so I'm going to just copy this one more time. So linear regression, actually, since this is a computer, can I just do a little lasso? Actually, why don't I just, I'll move these things down. I want all this stuff. This is what I need. Can I copy this? Nope. Okay, I don't know what I'm going to do. Let's just write underneath. We're just going to write here. So, for linear regression, we want to find the value of beta that minimizes the mean squared error, right? For logistic regression, we want to find the value of beta that minimizes the cross-entropy loss. And so really what we're doing is I visualize this in one of these Desmos things. So here is some data in purple. Here's some data in purple. And I have the computer calculates the mean squared loss. And I made it so you can slide the value of beta up and down. Okay, and this is the world's simplest example where there's only one parameter beta, right? Normally there's many parameters beta for each variable. Now there's just one parameter. So if you do beta equals 0.73, you get a loss of 2.5. And then you can try to make it better. So maybe if I go down a bit. Oh, that's making it worse. The loss is going up. Okay, let's try the other way. Loss is 1. Okay, 0.9. Oh, I went too far. Now it's getting big again. Okay, so maybe I try go like this. So I can guess and check, and for every value of beta, I can see what the mean squared loss is. I can try to make it smaller or bigger. That would be if a human was doing it. That's how a human would do it. Guess and check. How does the computer do it? Well, we need a better way to minimize a function. We need to think of some systematic way that would help us minimize this loss. And I put it to you, this is something you've hopefully seen before. If you want to minimize a function, it is useful to calculate the blank. The blank. And there's a nice one-word answer. Calculate the blank. So how does the computer do it? It involves this calculation. I'll give you 1 minute to guess what is the blank. Okay, let's see if you guys, what should we calculate to help us minimize a function? Let's see how your first year calculus class was. If you remember that you should calculate the gradient. Okay, gradient is great. Gradient or derivative. Derivative is in one dimension, gradient is in many dimensions. That is the right answer that I was going for. Calculate the derivative. So if you said gradient, also very good answer. Stochastic gradient is calculating the gradient in a funny way. Derivative, that's very nice. Differentiate, very good. So we're going to calculate the derivative. How does the derivative help us? Well, it tells you which way you should go. Let's go back to this picture, right? I was just guessing and checking, but if only I knew the derivative, then it would just tell me which way to go, right? So look, here is an example. I've just calculated it, and I'm going to turn it back on now. This is the derivative, and we're going to see how we calculate this in a second. Right now it says the derivative is negative 0.61. So the loss is 1.234. And the derivative is negative 0.61. So that means if I change beta by a little bit, if I change beta by 1 unit, then the loss should go down by 0.61. So should I increase beta or decrease beta? Well, I want the loss to be small, right? So if I want the loss to be small and the derivative is negative, then if I increase beta a little bit, the value of the loss should go down. So here I am. I see that the derivative is negative, and I can go up a little bit, and then the loss really did go down. And now the derivative is still negative. So I keep going up. I keep going up. Now the derivative is negative 0.01. So I can keep going up a little bit. And now I've gone too far. Now the derivative is positive. If I keep increasing beta, the loss is going to get bigger and bigger. So I've gone too far. I got to turn around. So by using the loss, and can I make it exactly 0? I probably cannot. Okay? It would be nice if I could make it exactly 0, but because of the way the slider is working, I'm stuck at 0.01. This is about as good as I can possibly do. Beta is 1.97. Here the derivative is 0. I'm right at the bottom of the loss. If I make it a little bit bigger, then it's worse. If I make it a little smaller, it's worse. This is the minimum. And that is what the computer does when you say, please run a regression. It uses the derivative, and it finds the minimum of the function by using the derivative to help it. One way is by doing what I just did. That is called gradient descent. So just move in the direction of the derivative until you find a minimum. In one dimension, it's just the derivative. In many dimensions, it would be the gradient. You can also find the 0 of the derivative using something called Newton's method, or variance of Newton's method. So there's many ways this is implemented in the computer, but in all cases, you are going to use the derivative somehow. So let's calculate the derivative, because it is not so complicated. So let's calculate the derivative. We know the formula. Mu hat is beta x. We know that the loss is the sum of yi minus mu hat. So really we have, combining these two functions, we have the loss function as a function of beta. If you tell me beta, I can calculate the loss. It's going to be the average, 1 over n data. And then we're going to sum up from I equals 1 to n data. We're going to do yi minus beta of xi squared. So all I did is I took this formula, beta x, and I put it in for mu hat, and that's the loss function. The loss depends on beta. For every value of beta, there's a loss. Now I can do the derivative. Do the derivative. dd beta of the loss. Okay. And this is, I know how to do derivatives. The derivative will pass through a constant, multiple, and a sum. The derivative goes through both of those. So you have 1 over n data. You have the sum from I equals 1 to n data. So the next thing we got to do the derivative of this dc squared. This is what you should have learned in the first day of calculus class. The derivative of something squared is 2 times the thing. yi minus beta xi. There we go, I did the derivative. Did I do it right? Yeah. Minus what?
Minus xi.
Minus xi, very good. So the chain rule, by the chain rule, you need a minus xi. The minus, by the way, I could have written this the other way. Let's simplify one step. 1 over n data. Let's write it like this. The sum from I equals 1 to n data. I'll bring out the factor of 2. Let's put the 2 in front. And let's just flip this guy around. So this is, actually no, let's leave it with a minus. I like it with a minus. Let's do a minus in front. So let's simplify. I'll put this 2 outside. 2 outside. I'll put a negative sign. Okay. This is a very nice. I moved the minus sign. So I put the minus sign on the outside, right here. Here's my minus sign from before. yi minus beta xi in our picture has a very clear interpretation. yi minus beta xi is exactly the distance between a purple dot and the line, right? Yeah. And I won't attempt to draw it in real time because I'm gonna have to debug it and it'll take forever. But yi minus beta xi is a positive number for all of the points that are above it, and is a negative number for all the points that are below. And then you multiply by xi. Xi is how far. If you're over here, then it's a big positive number. If you're over here, it's a big negative number. So we're multiplying how far you are from this line by how far you are over. And you can think of that as each point is pulling on the line, right? So each point says the derivative, for example, this point is going to pull up quite a lot on the line, especially when it's low like this. This is way too low. This point over here is saying, look, you gotta go up to meet me. I'm pulling you up. This point over here has a negative x value, so it's pulling down. So this point is trying to pull the line down. So the derivative is doing a very intuitive thing. You can think of it as every single point is pulling a little bit on the line and saying, come towards me. Come on, get over here, right? And the combined effect of all these points, added all up, is the derivative, is the total derivative. So every point individually is pulling on the blue line to try to minimize. And when you reach the balance point, when the derivative is 0, what does it mean when the derivative is 0 at this minimum? It means that the set of points pulling up, they're pulling up with the same amount as the set of points pulling down, right? The derivative is 0. These points are saying, please come down to meet me. These points are saying, please come up to meet me. And they're exactly balanced, right? We cannot go towards these points without sacrificing from the other points. Everybody is equally unhappy, sort of, so to speak. Okay? So it's a very nice formula. Beautiful formula over here. For linear regression, mwah, chef's kiss. Beautiful formula, easy to interpret. Okay. Any questions or comments about that? This is how when people program linear regression, they start with this formula, and they either find the 0 of this equation by using linear algebra or a Newton's method or something, or they use gradient descent and they just move in this direction over and over again to try to minimize it. Any questions or comments about that? Okay. Because the next thing we got to do, we're going to do it again for logistic regression. Okay? Same exact thing. But I hope you see this is going to be a little scarier, right? Why is it scarier? Before we had the squared function, what you learned in calculus first day, we had beta x. We did the derivative, we had to do chain rule. Aha, the derivative of beta x, it was x. Very easy. Now what do we have to do? Oh, we have the log, the 1 minus log. We have the sigma. Sigma has an e to the x, so 1 plus. This is a huge mess. A huge, horrible mess. Right, so sigma is e to the x over 1 plus e to the x. We're going to have to do the derivative of sigma. We're going to have to do this log and 1 minus log. It's going to be a horrendous nightmare. Okay, but there is actually, and I consider this in mathematics, there are maybe like 20 minor miracles. And this is one of them. This is one of the great minor miracles of mathematics, is that even though this thing, messy, bad, scary, ugly, this is ugly, this thing is ugly. When you go to do the derivative, the ugliness of this, by some miracle, cancels out the ugliness of that. I will tell you the formula for the derivative. If you want to read the derivation, it's online. But for the cross entropy loss, what is the formula for the derivative? And again, there's a lot of work to see why. This is a proper minor mathematical miracle. Minor miracle happens. And even though the formula for the loss is ugly, and the formula for p hat is ugly, what is the formula for the derivative? It is the same exact formula. And what do I mean by the same formula? It's yi minus p hat of xi times xi. So there's a whole bunch of ugly terms that cancel out, and you end up with the same formula. For linear regression, it was yi minus beta xi times xi. For logistic regression, it's yi minus p hat times xi. Oh, and with a minus sign. I always forget the minus sign. Okay, minus sign. So what does it look like? It ends up being the exact same thing. So here is the same kind of plot, but with logistic regression, minus 0.2. Let's do plus. So here I want x values going from minus 2 to 2, say. Plus 2. Minus 2. Y values I want to be minus 0.1 to 1, say. Okay, so here we go. So you have the dots are either zeros or ones, and this blue curve is the curve I'm trying to fit. Okay, and let me put on beta, which okay, I guess I gotta lower it to see. There it is. Okay, let me zoom out. So there's the value of beta. You can move it up or down to squish or shrink this thing. And just like before, you can calculate the loss. So you can always calculate the loss. Where did the loss go? Somewhere far away, I guess. Let's zoom out. There it is. Okay. Let's move these over here. So the cross entropy loss is negative 0.49. You can move this up and down, and it moves the loss. And just like before, you can calculate the derivative. And the amazing thing is that the choice of the logistic function, cross entropy loss came from coin flips. The logistic function is exactly the right thing to make it have the exact same interpretation as for linear regression. So you can think of all of these purple points. They are all taking the distance to the blue curve, and they're pulling in the exact same way that the linear ones do. And the point where we have the optimum value is exactly where they're balanced. So let's see, the derivative is what? Here the derivative is 0. Here it's positive, so I gotta go down a bit. So there we go, that's the perfect value. 2.02 is the perfect value. And at this point, everything is balanced. All these points on the bottom are pulling the curve down. All these points are pulling the curve up, and they're exactly balanced. And that is why logistic regression is so nice. Why do people use the logistic function? It's not because they made some arbitrary choice. It exactly works out to make the derivative super nice. And really, the thing behind the scenes, maybe I'll say one last thing. The reason this works is the derivative of the sigmoid function is equal to sigma of x times 1 minus sigma of x. This is some miracle fact about the derivative of the sigmoid, and that's what makes the whole party work. Okay, that's what makes this minor miracle work. And that's why people do logistic regression and not, some other function regression, is because it works exactly to cancel out the ugliness of the cross-entropy loss is exactly canceled out by the sigmoid, and you end up with this nice function. So how do people do it on the computer? When you say linear regression, it's using this formula. When you say logistic regression, it's using this formula. And then it does like a Newton method or a gradient descent to find the best parameters. But really, in all ways, it's very similar to linear regression. You can interpret the betas in the same way. They have the same error bars as before. The only thing that's different is the loss term, and the derivative is the same. Okay, so that is more or less how linear regression and logistic regression work in your computer. Now you've seen where they come from and like what they're actually doing. All of this stuff the reason I'm showing you, it is a precursor to how like modern machine learning works with neural networks and stuff. That's the same kind of thing. You always have a loss function, you do a derivative, and you always use the gradient descent algorithm. The derivative can be quite complicated. In the example I showed you today, the derivative was very simple. This example, even though I said it's very ugly, is still very simple compared to some big neural network. But if you understand how this stuff works, you will see exactly how it generalizes into neural networks, which we'll maybe do a little bit of at the end of the course. Any questions or comments about any of this stuff? Linear regression, logistic regression, coin flips, anything like that? Okay, let's stop there. Have a good weekend. Don't forget your draft is due tomorrow, so make sure you submit it and submit to the leaderboard your best model, and then you'll have peer review next week where you read each other's things and give some comments. Okay, see you guys on Tuesday.